Okay, you ready? Let's do it. You're listening to Chats from a Chair with me, Nick Dempsey, coming to you from my wheelchair. I speak with people who have a great story to tell, portraying the human potential, often in the face of adversity. Check out the Instagram page at chatsfromachair_podcast and let me know who you think I should have on and have a chat with. Also, don't forget to hit follow on whatever platform you're listening to this. But for now, sit back and enjoy this episode. Coming up in this episode, I speak with Professor James St. John, who is head of the Clem Jones Centre for Neurobiology and Stem Cell Research at Griffith University and is the lead researcher in the world-first human trial to find a cure for spinal cord injuries happening here on the Gold Coast, coming up in the next few months. So as someone with a spinal cord injury, obviously this is very exciting that this is happening, so I'll be able to absolutely bombard him with questions about the trial and exactly what's involved. So we'll be able to delve into a lot of detail in that. We also discuss his unique background in agriculture that led him to now leading this trial, as well as him giving an updated timeline on when it's going to start. So stay tuned for all of that and more. G'day and welcome back to another episode of Chats from a Chair. Today I'm joined by Professor James St. John. Mate, thanks for coming on and having a chat.
Oh, it's my pleasure.
Now, you are head of the Clem Jones Centre at Griffith University. What is the Clem Jones Centre?
Clem Jones Centre for Neurobiology and Stem Cell Research was started in 2016 from funding from the Clem Jones Foundation here in Queensland. They took our vision and said of creating a therapy for spinal cord injury, and they said, well, we'll give you some funding if you go out there and do it. So that's our mission, is to create a therapy and deliver it into the community.
Yeah, so the Clem Jones Centre, in collaboration with Griffith University and the Pericross Spinal Research Foundation, are working on a world-first human clinical trial to find a cure for spinal cord injury. What is the trial?
The trial is a cell transplantation therapy. We take cells, specialised cells from the nose, purify them, make them into a nerve bridge, which is transplanted back into the patient. And along with that, we have intensive rehabilitation, which is up for 1 year of rehab. Because once the cells start making those connections across the injury site, we need that long-term rehab to get those cells to make the right connections, get the threshold and make sense of it all.
It is very exciting that it's all happening. I mean, obviously myself as someone with a spinal cord injury and knowing so many people in the community, it's as I mentioned, a world leading trial to find a cure for, we'll use that word for now. We'll probably discuss more about how we're...
treatment is what I use.
Treatment for spinal cord injury. But yeah, it is very, very exciting, and it's all happening here on the Gold Coast, as we mentioned. So that, taking the nasal cells, there's lots of things to unpack in this because it is quite a complex trial. But how many people are being involved, and who's being involved in the trial to start with?
Well, there's two questions to that. How many people are involved in the trial? Involved in the managing of the trial and delivery of it is about 300 people, we think. We're still thinking on our to-do list of putting down everyone who's actually involved in the trial, but that's not a priority at the moment. But once the trial gets going, we're going to have people obviously participating in that trial, people with spinal cord injury. We're looking for 30 participants. 20 will have the cell transplantation, and 10 will go into the control group that does do the rehab. We need a control group to show that there's a difference from the regular sort of activities. And because the long-term rehab that we are wanting to do for this trial isn't routinely available in Australia, we need to have that control group to show that rehab alone we expect to have some sort of benefits, but we need to see that the cells have more benefits than just the rehab alone.
So there'll be some people that get the full nasal cells transplantation, and there'll be some that just get the physical therapy side.
Yep.
And you essentially track the difference between how much hopefully more beneficial, say, the nasal cells are than people that don't get it.
Yeah, but the priority for this first trial is safety and feasibility. It's very complex. We are asking people to do the rehab 3 months before the cell transplantation. We then have to take those cells from the nose, purify them, make them into nerve bridges, transplant them. A lot of this hasn't been done before. So we've got to make sure that the clinicians can do this, that it's safe for the patients. And then also we are looking at different types of injuries. So what injuries is it safe for? And then hopefully we'll see some that respond versus those that don't respond. And that will give us a lot of information about how we can improve the therapy into the future. So there's lots of things we've got to work out, along the way. So it's going to be, as I said, really complex.
Yeah, so that's sort of the overview for the entire trial. But obviously to get that overview, there's lots of little steps along the way to reach that. So I want to start with the nasal cell side of it to start with. So what is the process to extract the nasal cells? Is it a big process? Is it quick in and out? How do you get the cells from the nose to then be able to implant on the spinal cord?
Yeah, it's a pretty straightforward process. It's ear, nose and throat clinician, Brent McMonagle. He's the coordinating investigator for the trial. He's very experienced in taking nasal biopsies. It's a bit like a COVID test, I would imagine. You have to go right up high into the nose, and because it's uncomfortable, for those of us who've had a COVID test, it's not very nice. They'll be using general anaesthesia. It can also be done under local, but it's just easier if it's under general anaesthesia to get better access, because we want the best quality cells taken from the biopsy. And if it's uncomfortable for the participant, then that might impair getting the best biopsy. So the general anaesthesia, the process only takes about 15 minutes, which is just mainly going up and then excising the biopsy and then stopping it bleeding. It's only a small area that's taken. The beautiful thing about the olfactory system is that it can regenerate and repair itself. So there's no ongoing impairment to the olfactory or sense of smell. And from that, we can then purify the cells. But Brent has done this. He did a PhD on taking these olfactory cells, and he worked with Al Mackay-Sim for his PhD at Griffith University. So he's very experienced. Got great. Looked at different types of the biopsies we can get, different sizes, different areas. So he's in capable hands with his expertise.
Yeah, and does it have to be your own nasal cells, or can they be donated from someone, like say if a participant with a spinal cord injury for whatever reason doesn't have that healthy or effective of cells, can it be donated from a family member or someone else?
So at this point in the trial, we're looking for people who've got healthy noses.
Right.
It's very rare not to have healthy noses. If people don't have a good sense of smell, it's usually because of a blockage or things like that. But these cells themselves will still be okay.
Right.
And that's another reason why general anesthesia is used for the trial to get the biopsy, because if there is deviated septums or whatever problem the person might have, then Brent can go in, get past those blockages and get the cells. But coming back to your question about can donor cells be used, we're looking into the future for getting donor cells, because our therapy at the moment is looking for people with chronic spinal cord injury, but we have a vision and a hope that we can also apply this to acute spinal cord injury. So people who have an injury, they're in hospital, and a few days or weeks after that injury, we can transplant the cells. And in that case, we're going to need to have donor cells because we don't have enough time to get the patient's own cells for that really early treatment.
Need a bank of them sitting there to access and implant straight away. Yeah, okay. It's essentially if you can smell, you have the cells that can be used.
Yep. That's not to say that everyone's got the same quality of cells. And another part of the study that our lead human cell researcher, Mary Mataza, is doing is looking at the variation of quality of cells over time for different ages or different health status. But as we get more biopsies coming in, we can look at that sort of information.
Yep. Okay. And so you mentioned that the nasal cells are removed and built into a bridge. Sorry. So what exactly? How does that work? How do you take cells and build them
Yeah.
into a bridge?
Yeah, it is a fantastic invention that we have, and it uses biology, and it's a highlight of why it's important for um, Australia and the community to support discovery research before we get to these points of translational research, because by understanding how these cells grow at the basic level, we can now make these three-dimensional constructs. And so what we do is, um, you know, for those who've ever done biology or any sort of cell culture, there's not many of us in the community who do this, but we often will grow them flat on a plastic dish, and that allows us to see the cells with a microscope. And you can see each individual cell, but we're not cartoon characters. We're not flat, and so we grow in 3 dimensions, and so it's having cells flat doesn't give us the right information about how they behave. Instead, if we grow them in 3 dimensions, they have interactions all around them, they support each other. It's much better. It's harder for us to analyze them as scientists because we can't see them so well,
Right.
but they grow much better. So by having them formed in 3D, they are much healthier, they do their job better, they survive better when they're transplanted in.
Right. Okay. So then they're removed, built into that bridge, and that's when they're going to then be implanted onto the spinal cord at the injury site.
Yeah.
What's the time from, say, for the trial, someone to go in, have the biopsy taken from their nose, have the cells built into the bridge, and then to have the procedure to have it implanted on their spinal cord? What's the time process for all that?
So when we take the biopsy, we're going to be doing it here on the Gold Coast. That biopsy is then driven up to QGen, which is a good manufacturing practice facility in Brisbane at QIMR, Berghofer. And that's a specialised facility for production of cells for human transplantation. From that point, our team, which is a dedicated cell manufacturing team, work in that facility. They're fully gowned up, as you'd expect, to make sure that they don't contaminate the biopsy sample. The cells are separated out. We get rid of the cells we don't want,
Right.
keep the cells that we do want, and then we have to allow those cells enough time to proliferate, to expand and increase in number. We need 100 million cells. And that takes about 6 weeks for that process.
Okay.
Once we have those cells, we can freeze them in liquid nitrogen. And then they're ready until the patient is ready, the rehab's been done, the hospital's ready, the doctor's ready. As we know, people with spinal cord injury can have all sorts of things going wrong unexpectedly. Plus hospitals too, they have suddenly they have their surgery lists explode and they don't have time. So when everyone says, okay, we're going to be doing it next week, we can then take those cells out from the liquid nitrogen, thaw them, revive them, and then we can make them into a nerve bridge. And it takes us about 24 hours, 48 hours to make that nerve bridge once those cells are ready to go. So it's a really flexible arrangement in that sense.
Yep.
We need that 6 weeks to grow the cells, but after that, we can have them ready for whenever it might be that the transplantation occurs.
Yeah, okay. So absolute fastest would be 6 weeks.
Yep.
And do you know yet how long you could keep them there?
Yeah, good question.
Thank
We
you.
had a lab tour today up at our labs at the Gold Coast campus, and we had exactly the same question, which we haven't had before.
Right.
So two questions on the
Same day.
Yeah. So we've tested, Mariam's team has tested how long we can store them for, and at the moment we can store them for up to 1 year. We haven't gone beyond that yet. But we know we can store frozen cells, like human embryos, for in vitro fertilization aspects. They can be stored for years.
Right.
So it's perfectly fine, certainly up to 1 year. And there's always a small loss of cells when you freeze and thaw cells, but it's only a few percent. So it's you still get very good quality cells coming out at the end.
Yeah. Okay. And you said you wanted to get rid of the cells you don't want in there.
Mhm.
So not all the cells you'll take from the nose will be
No.
healthy, beautiful ones you want to use. You want to
Mhm.
need to separate them and get the healthy ones that are going to clean up and be more effective.
Yep, absolutely. So if you look at the history of olfactory and sheath and cell transplantation in humans, there are some unfortunate trials where they have put unpurified cells into the human spinal cord and they've got bad outcomes with inappropriate cell growth. if you put rubbish in, you're going to get rubbish out. So that's the key message from those ones. So our team has concentrated on having really high quality, high purity cell preparation, so that when we put them into the patient, we know that the vast majority of cells are going to be doing the job. I say vast majority. In biology, nothing's 100%. So I like to think it's 100%, but I'm a scientist, so I can't say 100%. They are doing what they're supposed to be doing. And we got rid of the cells that will have unknown consequences. So that's what the purification is needed.
Give the best chance for a good outcome.
Yeah.
And the cells on the spinal cord, so there's the bridge to essentially bridge the gap across the injury site, but they're also trying to clean up the scar tissue that is there. So are they essentially doing the two jobs of cleaning up the injury site and trying to repair that part, but also allow the message to get across? Is that right?
Yeah, so the beauty of our olfactory ensheathing cells, olfactory, as I said before, is a sense of smell, but ensheathing cells means that they ensheath, they wrap up nerve cells, but they do much more than that. They can, I'll go back to the role in the nose. So when we breathe in air that's full of odours, smells, and our nerve cells in the nose are directly exposed to the air inside our nasal cavity, and they can detect the odours. But in that air, there's also toxic chemicals and viruses and bacteria, and they can kill the nerve cells that detect odours. About 1 to 3% of your nerve cells that detect odours die every day as part of its normal process.
Right.
But they're replaced by stem cells that provide new nerve cells that grow back up from the nose into the brain and make new connections every single day. And it's the olfactory ensheathing cells that support those nerve cells in that process. So they remove those dead cells that happen every day, those 1 to 3% that die every day. They're removed by the olfactory ensheathing cells. Those olfactory ensheathing cells then help those new nerve cells to grow to their targets. They secrete these molecules that support those nerve cells to grow. They also secrete other particles that keep other cell types away. The nose doesn't want these immune cells coming in all the time to clean up the injury site, because otherwise you have constant inflammation in your nose.
Right. Yep.
So these cells have multiple roles. So that's why they've been thought to be useful for spinal cord injury. We put them in the spinal cord, they can help clean up the injury site, get rid of any dead cells that might be there, or remove chemicals that change the sort of environment. They can then secrete these molecules that keep the immune cells away to reduce inflammation, particularly in acute spinal cord injury. They can then secrete molecules that promote the nerve cells to grow, and they can integrate with the scar cells of the scar, because they've got properties that allow them to do that. And then they can form a physical surface over which the nerve cells can grow. Right. So they do multiple things, and that's why we think they're a great candidate for a therapy, because they're a living drug and they have multiple roles. If you have a chemical drug that's put in, it's going to have a single target.
Yep.
So you get one shot at hopefully making it work, and that's why that probably won't work on their own. By having the cells with multiple roles at different times, we hope to get good outcomes.
Yeah, it's interesting. It's obviously with spinal cord injuries. I was saying I had Jim and Jenny from Strides on the last episode, and I was chatting to them and saying the way that I generally try to explain spinal cord injuries is the fact that there's nothing really wrong with my body at all. It's just a little point in my spinal cord stopping that message getting through to deliver the message to the nerves in my legs to move or whatever it is. So, I mean, a bridge could grow across that and send a message from my brain to my legs. But at the point of the injury site, say at that exact point it went to my hands, would it be the case that maybe it'll grow across the bridge, get down, I'll be able to walk, but because the injury site itself is at my hands, they still won't work. But then obviously, as you're saying, if it cleans up that scar tissue as well, the hope is it does both, gets across the bridge, delivers a message to the legs, and cleans up where the injury site is to the hands, because otherwise, I mean, it would be good if I could walk, but not use your hands or one or the other. It'd be, yeah, it's just a funny thing in that sense.
Yeah, it's what we the human spinal cord is quite small. I mean, it's got but within that it's got multiple pathways. As you said, we control different parts of your body. And the beautiful thing about the nerve bridges is that we can implant, say, 6 to 12 nerve bridges into the spinal cord. And that means that clinicians can sort of place them where they think they'll do their best job, but also maybe target different pathways. And so we could get, theoretically, could get improvement in some areas, but not other areas because of that reason.
Yeah.
And we're looking into the future of then having a repeat sort of application where we can come back in and target other pathways for those that haven't responded just yet.
Will there be a difference between someone with a severed spinal cord or maybe just a pinched or compressed spinal cord, and difference in what the procedure will be, or with one would be seen as being possibly a higher success rate or something like that?
Yeah, absolutely. As we know, spinal cord injury is different for every single person. Even at the same level, the same sort of impact can have a different outcome. So we don't know. And part of this trial is to see what injuries respond and what don't respond. That's what we've got to find out. In our animal studies, we can have routine, consistent injuries, which is good from a science point of view, but that's not reality for humans. So that's why we need to try this therapy in humans to see the type of injuries that respond. And for those that don't respond to our treatment, we can work out how to make it respond.
Yeah, okay.
That's what the purpose is.
And the surgery itself, obviously the spinal cord is so delicate. The surgery itself, how do you, I guess, guarantee that is safe, or that it's not going to cause more damage to something?
Well, I'm not a neurosurgeon, so for me it sounds like it's a really complex process. But our neurosurgeon, who's the principal investigator for the trial, Wayne, he's confident this is a straightforward procedure. I mean, a neurosurgeon, they can do really complex brain and spinal cord surgeries. They can cut cancers out of people's brains, and that's really complex. So in this one, it is invasive, absolutely no doubt about it, and there's obviously associated risks with any sort of invasive surgery. But it's a matter of exposing the spinal cord and then placing the nerve bridges in. There's not much more manipulation than that. They may take their clinical expertise opinion and think about maybe removing some of the scar tissue if that was appropriate, just to get access. But then the nerve bridges are just glued into place. That process itself is quick. Previous and other current clinical trials using cell transplantation for spinal cord injury can use micro-injections, where they take a little needle and they inject into the healthy spinal cord above and below the injury site. And because they have to do it so slowly, those injections can take hours. Right. And they can do hundreds of little micro-injections just to get enough in there. So that's a much higher risk process. Our one, where we can just open up the spinal cord, put the nerve bridge in and glue it, that process should be pretty quick. I mean, I haven't done it myself, but I can imagine it might only take 15 minutes or so for the surgeons to implant it once that spinal cord is exposed. The whole surgery will still take several hours. Yeah. That's mainly the preparation of it, to remove the muscles, expose the bone, and then replace everything back in place. That's at the end of it. But the actual transplantation is straightforward and quick and minimally invasive, and it's been designed for that purpose, just to reduce risk.
Yes, speaking to some of the neurosurgeons that are ready to do it, they're ridiculously relaxed about it, aren't they? They're just like, no, it'll be fine. We can do this all the time.
I mean, I sort of joke about it. It's like neurosurgery 101. I mean, apologies to the neurosurgeons out there, but it doesn't seem to be complicated from their point of view. It's fingers crossed that it's what they'll say afterwards too.
Yeah, they're a different breed, the neurosurgeons, aren't they? But they can also 3D print the spinal cords now and ahead of time, so have a more of an idea exactly of how to build the bridges as well, to have even more accuracy. Yeah.
So I forgot to say before about our Clem Jones Centre, we've got an incredible team. We've got 40 people in our team, and we've got all these different backgrounds. Got cell biology, surgeons, molecular biologists and imaging specialists. One of those people is Ronak Reshamrala. He's a medical doctor from India. He's now a researcher in our team, and he's worked out how to print these 3D spines to de-risk the surgery, to allow the clinicians to help plan that surgery and also to educate the people in the trial about what their spinal cord looks like. So he can take an MRI image of the person's spinal cord and then convert that into a 3D printing file, and then 3D print. Along with Josh in our team is brilliant with equipment and technology. He can 3D print a file. And we also work with the Advanced Design and Prototyping Institute at Griffith University. You've got really advanced 3D printing systems. But we can 3D print the spinal column, the bones, and the spinal cord with the injury site as well. So that allows and it's life size. So that means that the clinicians can use it to practice their approach, so they know what the injury looks like before they get in. Because the last thing they like is to have surprises when they do surgery.
Yeah, it's crazy.
So if they know what they're probably going to get, they're much happier. But they also can plan where they might put those nerve bridges into the injury site, so they can test beforehand, because we actually have the actual cavity. Most people have a cavity where their injury site is, and so they can practice where those nerve bridges will go, and then that de-risks the surgery, and hopefully reduces the time for surgery as well. But then the person who's having the person with spinal cord injury can actually see their own injury site. They can understand what's going to happen, so it's good for their education.
That'd be cool.
Yeah, absolutely.
Yeah.
But also at the end, we can do another scan, another MRI, another 3D print, and you can see the changes.
Oh, true, and see if there's been some scar tissue cleaned up or whatever it might be.
Or whatever you might have seen, it's reduced. And maybe, hopefully, we're hoping people will have improvements. But even if they can't feel something, if they can see that things have changed, then that gives us hope that it might, with further rehab or maybe with an additional transplantation, we can then get ourselves on that path to recovery.
And you've had promising results in the lab in
the preclinical animal models?
Yeah,
absolutely. So the outcomes are great. We get unfortunately we have to do the testing on animals because we need to show safety on those animals, and they've got great outcomes. Another good thing about our team is that we've got credible people who can do very good animal care. By having great quality animal care, we get good outcomes. And also from an animal ethics point of view, we've done enough work on animals, so now it's time to move to humans. But we get great outcomes. We can see that the animals recover from being paralysed, motor, sensory and autonomic function. And with our new quality of nerve bridges, pretty much every animal gets recovery of some function. It's hard in animals to target particular pathways. So we get variations between the animals because of where those nerve bridges might be effective. That's why it might be easier to get outcomes in humans, because it's bigger. The clinicians can target different pathways with ease.
The other thing I guess easier in humans is to put them through physical therapy and get responses from them in that sense. So I want to focus on the physical therapy side of it now, because that is, again, a huge part of it for, is it a year-long worth of therapy? So what is the outlined process for the physical side of it for the trial?
So we're asking people to do 3 months of prehab, so rehabilitation before the cell transplantation. And we want people to do that because maybe they haven't done rehab before, or not for a while, so we want them to get, maybe they have, haven't had the opportunity of having some natural recovery through rehab. So we do some rehab for that purpose, but also to get them fit and healthy for cell transplantation. Because even though it's a straightforward procedure, the healthier you are for a invasive surgery, the better the outcomes. So it's 3 months of prehab, cell transplantation, and time for recovery of several weeks after that, and then back into rehab for another 8 months. And throughout this whole process, the 3 months before and 8 months after, we're asking people to do 3 hours a day, 5 days a week for all that time. But we also know that people have lives, jobs, and maybe that's too much for some people. So in that second part with the 8 months after the first 12 weeks or so, people can reduce the amount of days down to 4 days or 3 days if they prefer. But from a neuroscience point of view, we'd want people to keep on going as much as possible, because the more you do, the more chance of success. but we do allow people to drop off if that's a better fit for their lifestyle.
So you envision that just having the nasal cells or the cells transplanted won't be enough. We'll just get better results with the physical therapy side of it. That's why it's so important to try to reconnect and create that connection with the brain.
Yep, absolutely. From a neuroscience point of view, it's again where discovery biology is really important. I spent a lot of my early career looking at how the nervous system grows. And so nerve cells, when they're first making our whole bodies, they'll go to many different spots. They'll sprout and go everywhere. Some will get to the right target, and those ones then have to get the threshold. The ones that don't go to the right target get pruned away.
Right.
But that's only through reinforcing those connections. So the ones that survive versus don't survive, it's through reinforcement of those connections. So when we repair the spinal cord, if we don't tell the nerve cells that they're in the right spot or the wrong spot, we won't get that refinement of messaging. So we really need that rehab. So from a neuroscience point of view, you need that rehab.
I've heard stories of human body, like it wants to adapt and find that connection. I've heard stories about where a valve has been blocked and it's created a new pathway around it so it doesn't have a heart attack and things like that. So it's like your body wants to create that connection. So by giving it everything it needs there, or the cells it needs, and then the idea is try to connect your brain. So if someone's cycling my legs, I'm thinking about that, and as if I'm doing it, and the message sending from both ways up the spinal cord is hopefully they're going to just connect.
Yep. There's a lot we don't understand about how the nervous system can remodel itself. And we're only just touching the sort of the basic understandings, really. And certainly no one has repaired the spinal cord in a way that we know what sort of rehab's going to work. So that's why we need to be flexible in our approaches and our thinking. But certainly from my point of view, if we just transplanted the cells and didn't do rehab, it'd be a huge waste.
So how long after the procedure do you monitor the patient before a conclusion's made about whether it's successful or unsuccessful or whatever it might be?
It's a great question, because we're going to be, unfortunately for the people on the trial, we're going to be doing lots of assessments, just because spinal cord injury is so complex. So we're going to be looking, patient journey is about 1 year, from the start to the finish. We would hope that improvements will continue on after that, but from the patient assessment point of view, it's a 1 year journey.
Right, and then so if they, say, 18 months down the track, started showing improvements, would you include that in reports or whatever it might be, or could that just be coincidence, or what's that seen as?
Yeah, so it's not going to be part of the formal analysis, but we can certainly have follow-up or longer-term analyses, and that can be part of a separate sort of a study later on. But we're not including that long-term follow-up at this point.
Yeah, okay, I guess if 5 people see 18 months down the track they have improvements, and you start seeing a correlation in that, then things can be adjusted.
Yep.
A lot of this is, at least to start with, going to be done at Making Strides up here on the Gold Coast, and a lot of different physical therapy sides of it and things that they will implement in there. But do you envision the therapy being used alongside some of the emerging interventions like electrical stimulation and things like that?
Yeah, so part of the program is that functional electrical stimulation can be used, but in addition to that, we know there's all these other types of rehab becoming available, assisted devices and stimulation and bypasses that can be used. Absolutely. We are not prescribing the rehab, what should be used. We're saying we don't know what rehab's going to work. We're going to leave that to the experts, the rehab providers, which is Making Strides here on the Gold Coast, plus also Royal Rehab in Sydney and the Next Step in Melbourne. They've all got different approaches, and which is what we want. We want to see what works, and also they suit different types of people. Some people like the high-end equipment and facilities that Royal Rehab might provide. Making Strides is more that sort of high-energy gym place, and the Next Step's got great sort of holistic approach and a different again. So it suits different people, but we don't know what rehab. And so between each participant and the rehab providers, they work out their own program. So we're not, as I said, we're not prescribing what people should do.
Yeah, and do you think time since injury will influence the recovery rate if there's perhaps motor neurons have already started to degenerate a little bit more in some than others?
So from a biological point of view, logically it'd be better, we get better outcomes if we treated people soon after injury. And we do think our therapy is very effective for treating acute spinal cord injury, but because of safety reasons, we don't want to go there just yet. Maybe in the future after this first trial. How long after injury? We don't know.
Yeah.
When I started my career in this area, it was impossible to repair the spinal cord. It's just a pipe dream. It's never going to happen. It was never going to happen, what people said. But now we know it can be done. So if we start saying, well, there's no point doing it after 10 years, we might be wrong.
Yeah.
Why not? Why can't we repair the spinal cord after 50 years of injury? It might be possible. And so in our trial, there is no upper limit for how long after injury. We're just saying to start with at least 12 months after injury, but we will consider people have been injured, for decades if that's those people are suitable for inclusion in the trial.
Especially, obviously, after perhaps you'll find something in this trial that then able to improve the therapy overall and stretch out how long it can be.
But as you said, the longer after injury, the more degeneration may have occurred. So it might be a harder ask to get there. But we're being open-minded and saying, well, we don't know.
What results would you need to see throughout the trial to consider it a success?
Great question. For us, because it's a safety and a feasibility trial, if we don't have adverse events or serious adverse events that indicate that we're doing damage, unacceptable damage, then that's a success. So if we show that we can implant the cells, we can purify the cells, implant the cells, and people recover, but we don't get any functional outcomes, that's still success. Why is that the case? Because we are dealing with chronic injuries. Maybe it's too long after injury, possibility number one, or we might have just picked the wrong type of injuries. We don't know what type of injuries respond versus don't respond. But if we can learn from what is happening in the trial, then we can improve it into the future. As I say, we could maybe treat earlier, we could increase the dose, we could maybe activate the cells in different ways, or pick specific injuries that might be more amenable to repair. That's at the minimum.
Yeah.
Beyond that, if we get improvements in function, we'll be happy.
Like I said, obviously, even if as you said, you get nothing, that's still a result to say, okay, well, what we did didn't achieve anything.
Yes.
That's still a step closer to finding what does work.
Yeah.
So,
and certainly the way we are implanting the cells in a nerve bridge, we should get better cell survival from our point of view. And maybe that, well, worst case scenario, our cells aren't the right cell type.
Yeah.
But maybe some other research group out there has a better cell type or a better sort of condition that they can use our nerve bridge approach. So therefore we can use their cells with our nerve bridges to get a better outcome that way too. So there's lots of positives we can get out of it if we get a complete sort of zero outcome.
Yeah. It's a funny thing that, I mean, hopefully that doesn't happen. We get great things,
right,
but it's still a success. Yeah.
But unfortunately, history says that a lot of clinical trials don't progress because they don't get the outcomes of positive outcomes. So we are making sure our expectations are that safety is number one. That's our primary outcome of this trial.
And in line with the safety, there's people or certain injury levels you're looking at more so than others, just for initially in the trial to reach that safety.
So again, we're looking for diversity and it's safety first. So we're going to be starting with people the first people will be lower level thoracic injuries, or not lower, but thoracic injuries, and then we'll go higher up after that, stepwise sort of in terms of safety. We'll start with complete AIS A and B injuries, and then we'll go to AIS C injuries. So it's a matter of slowly going through that safety aspect. The reason we're starting with AIS A and B injuries is because worst case scenario, if something goes wrong, hopefully we can't make an AIS injury worse. So that's why we're starting with those injuries. Unfortunately, we can't go C4 and above at this point because of the risk of complications with respiratory function. So the clinicians have said that's at this stage an unacceptable risk. If something goes wrong, we can make someone severely disabled by affecting the respiratory function. So we'll think about those into the future, and hopefully we can treat those higher level injuries into the future. But it's a matter of severe injuries going towards less severe injuries, longer term injuries. And now as we go through the trial too, we can be recruiting people who have injuries up to 4 months after the actual primary injury. So we go earlier as well. So we're looking at that sort of range of types of injuries.
I guess you have to start somewhere, don't you?
Yeah.
Then it can be.
And we're deliberately going for diverse here. That's why the trial's bigger. Originally, we wanted just to have a smaller cohort, but then feedback from the scientific community worldwide was that our trials in the field have been too small. If you only have 4 people and none of them respond, is that because you just got 4 people who don't respond?
Yeah.
So by having a bigger trial, hopefully we can find people who respond versus don't respond. And other trials have taken people with exactly the same injury level, thoracic level 10, for example. What if they're picking the wrong injury?
Yeah. Right.
We don't know what injuries respond. And also from a safety point of view, if you do it, everyone has the same injury level, well, how do we justify then going to higher or lower after that? Particularly, high level injuries. So we need to look for safety in this first trial, which is why we need this bigger trial design.
So gathering a lot of information and a lot of data to move ahead with. Let's say the trial is a huge success. People gain physical movement, they gain all different things. What is the next stages to take it to the masses and make it available for all people with spinal cord injury?
Yeah, absolutely. So once we get our approvals, we can talk about approvals in a moment for this trial to start. A lot of my hard work, and Andrew Rayfield, who's the guy in our team who does a lot of the admin. So Andrew's he'll be really happy when we have the approvals because he can stop looking through all the wording of our applications. And we're going to start immediately looking at the next step, the next trial, because it takes planning. It takes years for planning, but we also have to get partners. This first trial is going to cost in excess of $15 million or maybe $17, $18 million once we get to the end of it. The next trial is going to cost $50 to $100 million.
Right.
And that one will be looking at efficacy, so looking for showing that the therapy can improve function. And then beyond that, the next trial will be a phase 2 trial. Then there'll be a phase 3 trial. A phase 3 trial is multinational trial, so you're going to have sites in different countries, much bigger pool of participants, and that trial can be $500 million or so, or $1 billion. Very expensive, and for that we need to have multinational companies coming in to invest in it. So we are looking at that whole pathway, which partners are going to be interested, and we're starting those conversations as soon as we have the time, which is as soon as we have approval for the first trial.
Right, yeah, okay. So if you're really rich and listening to this or watching this, feel free to throw some money in this.
Right.
Okay, so the big question then, when does this start?
So
the approvals.
Yes. I keep saying soon. I'm so sick of saying soon. We are hoping for the final approvals in the next week or 2 or 3. The reality is we've resubmitted everything back to the hospital for their checks. They've got to make sure that everything is in place. We've had some small delays with, again, legal questions about insurance, which I think have been solved. The budget is being gone through the process of being checked again, and we're just waiting for final confirmation of who's involved and what sort of aspects of the project, because you can imagine it's really complex, and the principal investigators want to know exactly who is doing what and who's responsible for what every single day, so there's no hiccups. Once that's done, I'm hoping we get approval.
Okay.
But until I get that, until someone else comes up with another suggestion, what about this? That's what we've been delayed with. And then, of course, now it's school holidays, so people are
Yeah.
not always available to finally sign it off or pass it on to the executive for signing. So hopefully soon.
That's the thing that keeps happening. It's currently, as we're recording this, early July, and look, we've had many discussions where it's someone's away on holiday or someone wants one more question, and then those things on top of each other, waiting for someone to reply to an email. They do add up. That it's getting there. It's getting closer every day.
I should say that the Gold Coast University Hospital, the people there are doing a fantastic job.
Yeah.
They really want to make sure it's right. And they have to go through all their checks and balances. Same with the university, and we've got a contract research organisation, Excelligent, who are absolutely brilliant. And they've been going through, word by word to make sure there's no ambiguity. And there's some great people who've been making sure that it's all right. They have to do their job really well, because otherwise the executives won't sign off on it.
Yep.
And so they are advising the executives at the hospital and the university that, we've done all our checks, you can sign it, and then hopefully that will get done very soon.
Yeah. How did you did you have experience with people with spinal cord injuries before this, or how did you come to want to do this?
That's a great question. I've asked myself, how did I end up in this spot? So my background is weird. And that's a good thing. When I was in school, I liked science, but I didn't know what that meant really. So when I went to university, I did agricultural science because it was really broad.
Right.
It's about doing animal biology, cell biology, soil biology, environment, along with economics and management in a holistic way with unexpected variables. It's really complex agriculture. And my dream was to work overseas in agriculture, particularly in developing countries, and blah, blah, blah. Life gets in the way of things. And the reality was that there's a lot more money in biomedical research than there is in agricultural research. And so when I finished my PhD, which is in agriculture, I was offered a job to work on carbohydrates. My PhD in agriculture was working on carbohydrate metabolism in pasture grasses,
right?
In Victoria, in the south of Australia, southern parts of Australia. And just to explain that point of view, when sheep graze the grass over summer in those temperate regions, the grass is dry. It's their dry season, and they don't get much nutrition from it. So if we could increase the carbohydrate content, the sugar content of grasses, the sheep will get better nutrition. They can digest their dry feed much better, and they won't lose weight.
Right.
There we go. It's a bit of agriculture 101.
Yeah.
I got then offered a job to work on carbohydrates in the olfactory system in mammals. And I had no idea what a brain was,
Yeah, right.
I worked on grasses and carbohydrates, but I could work on carbohydrates. That's the key. So in the olfactory sense of smell, each nerve cell that detects an odor has a specific carbohydrate signature that tells us where to go and make a target in the brain.
Okay.
It's really, really complex. Carbohydrate mapping is called. And so I started working on how carbohydrates help the nervous system create this map of the sense of smell. And I loved it. And I was learning things. And the beauty about me being, from a weird background was that I didn't know what I was doing. And I didn't follow dogma. I didn't have a textbook where I was taught that this is what happens. I came in with just new ideas. Open mind.
Yeah, right.
And I loved it. And I remember when I started off, everyone's looking at nerve cells because, as we know, to repair the spinal cord, you've got to get those nerve cells to make connections. And so the whole field was looking at how do we get nerve cells to grow and guide them and make them turn and stop and all that sort of stuff. And I was using live cell imaging, which is really early, because when I started my research career, to take a photograph, you couldn't use digital cameras. You had to have film in a camera.
Right. Yeah.
And so you had to put on top of a microscope and you had to push the button, take a photograph, and then you had to go and actually develop it yourself. We had labs where you could dark rooms where you develop your film.
It would have taken a bit longer.
Yeah. And then someone came up with this brilliant idea of making digital cameras. You could put it on a microscope and then you just, you could just take photographs and see them straight away. And then you could do live cell imaging. Because before you couldn't do that because you had to take a film camera.
Good idea.
And so I was there at the advent of digital imaging, which allowed us to do live cell imaging for the first time. And I could see things that other people didn't see. And I realised that to get a nerve cell to grow, you had to get the supporting cells, these glial cells, to do their job. In fact, the nerve cells were following the glial cells.
Right.
And for me, it was like, it's a light bulb moment. To repair the nervous system, you got to get those supporting cells to do their job. It's like, when you're on a motorway, a bridge falls down. You can't get the cars crossing that bridge until you repair the bridge.
Yes.
So that's what these supporting cells do. They create that pathway which the nerve cells will grow across. And so then I switched into concentrating on how the supporting cells can do their job.
Right. Yeah. Interesting.
Here we are now.
Starting from sheep eating grass to then repairing the spinal cord. It's a bit of a change of career, isn't it? But it's interesting that, like you said, just that pathway of one thing led to another, and now if you hadn't have started with that where you did, that would be a very different outcome at the end. Yeah. So it's very interesting. Everything happened for a reason that way, didn't it?
But I should say it's also through lots of other things, the funders too. So when I started my career, everyone got funding from the federal government for National Health and Medical Research Council. The success rate was like 33%, very high. Now success rate for government grants is less than 10%. It's really tough.
Right.
But the government said, go out there and get money from elsewhere. And I listened to that and thought, well, okay. And that's where the Pericross Spinal Research Foundation and other great philanthropic organisations support us, because they give us the funding that gets us to that point where we can then get government grants. Yeah. You can do that sort of groundwork, get the data that then convinces the funding bodies to further support the work. And people like Perry is fantastic. He gives us carrot and stick approach. Here's some money, but hurry up and get some results.
Yeah.
And we love that because that makes it real. We understand that this is coming from donors who have an interest in this one. They want to see success, and it just feeds upon itself. We get excited because the community is excited, and it helps us get the best results.
Now that you've worked so closely with people like Perry and others in the spinal cord injury community, do you feel a sense of pressure or to make this work?
Yeah, absolutely. I often think, if it's a sort of responsibility. I mean, I've been lucky in that I've been given a fantastic education here in Australia. And it shows that, if you've got that interest and you've got that sort of networks around you and support, that you can create ideas. But what's the point when there's a purpose for it? There's lots of great research out there that maybe doesn't have a definable outcome at this point because it's discovery research. But at some point, to translate it becomes exciting. It is exciting to think that we can change people's lives. And also this responsibility, because of my over 25 years of knowledge of, not 25, oh my gosh, almost 30 years now. I'm getting old, aren't I? Of knowledge in this area. Am I the world's leading expert in this? Probably am. If I didn't do this, well, who would do it? So I have to keep going because, this could very well work. We're going to give it our best shot. I probably don't have all the answers yet. There's going to be some young people coming in. We've got great people in our team. We've got brilliant ideas already. They might be able to take it even further. Hopefully, improve it into the future. But we have a responsibility of keep on going because, this might just work.
Yeah, well, I mean, it's such a thing in life with any situations just to have some hope and hope to look forward to. And I think, like you said, with so long with spinal cord injuries, there just hasn't been any hope. Just people said it wasn't possible. It can't be done. So, I mean, in the least, it's given excitement and things that, like you said, this could just be the first step where you might get incremental improvements, and years down the track it might improve more. But it has to start somewhere. So it's very exciting at the moment of what is happening. So you should feel pressure from me. No, doing great work. But, what message would you like to send to someone that has a spinal cord injury and might be interested in learning more, or maybe putting their hand up for the trial when it opens up?
We're very keen to hear from everyone in the community. It helps us understand the demand for the therapy. Part of future funding is the investors want to know, well, how many people would actually do will put their hand up for the trial. So if you're interested, we're keen to hear from you. We will be opening up expression of interest once we have our approvals. We'll be advertising widely. We've got a website ready to go. We've got a holding page for that one, which will become live. And if you don't quite fit all the criteria, please just put your information in anyway, because that will allow us to understand, well, if we changed our selection criteria, we could then make it appropriate for other people too. And if you want more information, again, come to our website. We also have lab tours. If you're visiting the Gold Coast, we have lab tours once a month or more often if there's demand for it. We can come and see the research firsthand and ask us questions.
They're great, the lab tours. Yeah, there's lots at Griffith University on the Gold Coast. They're on the Clem Jones website. I know they're on the Perry Cross website as well. Go on there and you can book a lab tour through there and find out when they are. And they're great as well. So, and the website for expressions of interest, that'll be through the Clem Jones as well. Yeah,
through our university website.
Yeah, there's all social media pages as well. The Perry Cross page on Instagram and Facebook and Clem Jones and Griffith. I'm sure they'll all be shared across there as well. But there's lots of exciting things happening here on the Gold Coast with Griffith and Clem Jones and Perry Cross Foundation. But it's all very exciting for, I know, people within the spinal cord injury community and people you talk to. Everyone, it's all people are talking about at the moment, and obviously it is so close, but it's very exciting. So a lot of the work that you do and that the Clem Jones Centre and all of the people you mentioned do, it doesn't go unnoticed or unappreciated from the people in the spinal cord injury community. It is very exciting. We do appreciate and love everything that you guys are doing. As I said, it does give hope, a lot of hope to what the people are living with every day. So even if it's the most incremental improvements, whatever it might be, will be massively life-changing to lots of people and their families and community that are around them. So thank you for all the work you do and your team, and hopefully, continues on.
Yeah, great. Well, hopefully we get this trial started soon.
Let's get us up running again.
Yeah, that's right.
Thanks, mate.
Okay, thanks,
Cheers.
Nick.
Well, massive thank you to Professor James St. John for coming on and sharing all that information. Obviously, it's a lot that goes into it, but he was able to break it down extremely well. So thank you to him. And if you are someone listening to this that is interested in donating, please reach out, because as he mentioned, to be able to take it to everyone with a spinal cord injury, it is going to cost a lot. So please donate if you can. And if you're someone that wants to find out more about this trial or about the research, you can head to the Clem Jones Centre for Neurobiology and Stem Cell Research, or to the Perry Cross Spinal Research Foundation. Both of their websites have plenty more information, as well as being able to look at attending a lab tour where you can actually see the nerve bridges that we spoke about and where all the research is happening. If this episode or any of my episodes do bring up any adverse feelings for yourself, please contact Lifeline for support on 13 11 14. You can also send them a text message on 0477 13 11 14, or go to lifeline.org.au and navigate towards the live chat. Remember to reach out and check in on each other, and that it ain't weak to speak. Also, don't forget to go check out the Instagram page at chatsfromachair_podcast, or the Facebook page at Chats from a Chair Podcast, and let me know who you think I should have on and have a chat with, and also check out all of my past guests where you can catch up on episodes you might have missed. But that's it for now. Hope you enjoyed this chat as much as I did. Cheers.